we were working on concave mirrors, right? Okay, everybody, concave mirror. Because I'm drawing it from the left, I'm assuming the left side is my mirrored side. Could they redraw this with stuff on the right? Yes, they could. See, please be careful, because they can do that. They've been trying to change things up a bit on the test to make it look new. And most books show them on the left. Okay, so if they show it on the right, no big deal. It's the exact same picture, just flipped over. All right, what's this point called again? Focus. And the distance between here and here is called the focal length. Okay, this spot right here actually has a name. This spot right here, where the mirror crosses the principal axis, it's called the apex. All right? It's called the apex. They rarely use that, but in case you hear that term, the focal length is from the focus to the apex. Okay? All right, this spot right here is called the center of curvature. All right? Now, I don't believe we talked about this last time, the geometry of all this stuff. All right, the focal length right here, from the apex to the focal length, is also called F, so please be careful. When they say F, they might mean an actual length in meters, or they might mean a spot in front of the mirror. Okay? You can usually figure that out pretty easily. The center of curvature, is twice the focal length. Okay? So sometimes it's just labeled as 2F, but it's twice the focal length mathematically. All right? What's that?
Is that equal the radius of the...
Yes, and so this distance from here to here, or from the center of curvature to the apex, is the radius. Oop, I put radius. Okay. Now, here's a common question that they'll ask on the test sometimes, just to see if you're kind of paying attention. So you have a big concave mirror. You take it outside at night, okay? And the moon light shines on the mirror, and it bounces off the mirror and forms an image. That is, say, 20 centimeters from the mirror, okay? So you got your big concave mirror, the moon's way out here, a pancake-shaped moon, and it forms an image of the moon right here, okay, at 20 centimeters, okay? Now the question is what's the center curvature of the mirror? Okay, we got to vote, James, for 40 centimeters is his guess. Why would that be a good guess?
Because the light is parallel.
Okay, why is the light parallel?
It's infinitely away.
Because the moon is very, very far away. Okay, does everybody see that if I have a mirror right here, and if the sun is right here, that light rays from the sun that hit this mirror are at wide angles, right? But as I move the mirror farther away from the sun, that the angle that hits the mirror gets smaller and smaller and smaller, right? And that is certainly not parallel. That's getting closer to parallel. That's even closer to parallel, right? So the moon is a long distance away. So the light rays that come from the moon that hit this mirror are going to be parallel. And since they're parallel, they're going to cross through the focal point. And the focal point's at 20, and the center curvature is twice that, right? The center curvature would be 40. Does that make sense? So anytime, how many of you, when you were little kids, let me put it this way, and you had a magnifying glass, you took the magnifying glass outside, and you tried to burn ants, or you tried to catch things on fire, you began your career as a pyromaniac, okay? How many of you tried that? And you saw a little dot, a really bright dot, right? Okay, that dot forms from the parallel light rays coming in and going to the focus. Now that's a lens, we'll talk about that in a minute. Okay, you can do the same thing with a mirror, okay, except your dot forms out above the mirror, all right? So, and by the way, why is that dot round?
Because it's a circle.
What's a circle? Nope. If you had a square lens, it would be a circle.
The sun.
Because the sun is a circle. Because what you're seeing is an image of the sun.
So
Now,
we had a square sun.
if we had a square sun, it would form a square dot. Now, if you don't believe that, here's what you should do. The next time we have a partial eclipse, go out there with your magnifying glass and try to catch something on fire, and you'll notice that the image that's formed is not a round dot. It will be a crescent shape. Or you can go out at night. Okay, it's a little harder to do around here because there's lots of lights around. But if you do this at night, and you have like a half moon, all right, you can form an image of the moon, and instead of getting a dot, you'll get a half moon. You'll get this shape. Okay? So it's forming an image. All right? Okay. Let's finish out these ray diagrams. Let's go on to the interesting ones. Actually, let's do a quick review of the different images that are formed. Let me write them up here on the board. They go like this. Mirrors. Okay, we have a plane mirror. A plane mirror forms an image that is the same size and same location, but behind the mirror. Right? So if I put something up in front of the mirror right here, the image that will form will be back here. And the distance D is the same, and the height H is the same. Got it? And what kind of image is it?
Virtual.
Virtual. Virtual and upright. Okay? Virtual and upright. Okay. Now, we have started with this kind of mirror, which is a concave with light coming this way. Okay, concave. And so far we've formed quite a few different images. And let me do a quick review.
Me too.
Two, that's it? All right,
Yeah.
let's draw them.
We're pathetic.
We're not pathetic, not yet. Okay, so we started off with a person up here, I think, and light came off this person, came through here, went through here, came out here, and went through here, and we formed a little tiny mini-me right here. Alright? We formed mini-me. Okay, this image, when the object is out here, we form this image. Okay? So, what is the properties of this image?
It's inverted.
Inverted.
Real. Between C and small.
Inverted real between C and F and smaller. Very good. Alright, and then we did this one. And this is probably the hardest one to draw, or next to hardest one at least, where you have something right here on the focal point. Not on focal point, on C, sorry. And so your light ray comes in, goes through here, comes out here, and then you end up with a little house the same size and location. It's inverted and real. Okay? When it's on C. This one's beyond C. Okay? So if you start beyond C, you get this. If you're on C, you get this. Okay, so let's go on next one. All right, no more review. New. Okay, this time. What's that? In between.
Fred, where's the ruler?
Anybody have a ruler? Any extra rulers laying around? You got them right there? Excellent. Thank you.
Can you make the object asymmetrical?
You can if you want.
I mean, can you?
Can I?
To make it.
You mean like the front, the back? Asymmetrical?
Yeah. So. Otherwise, I'm not sure, like, if it reflects or if it just.
Like here.
Yeah, like that.
Okay? There you go. So we got a flower this time. All right? Now, notice how we're always starting at the top point up here? Because anything that's on the axis right here is just going to reflect off and come back along the axis. The one that goes through the focus comes straight back. The one that hits the mirror and comes back through the focus, one that's parallel. They're all along the axis. So the bottom of the pot is going to be on the axis again. So that's why we only draw this top spot right here. So right this top spot right here. Where is it going to be? All right, what rays do I draw again?
Hits the mirror.
In the mirror, and then where? Through the focus. Got it? Okay, what next? Goes through the focus, and then bounces out parallel. Ooh, mine's going to be way off.
Ooh. Where's it supposed to be?
I'll show you. I'll show you my drawing. I'm doing it freehand, so mine's going to be way off. Let me draw my mirror. I've had my mirror curved too much, maybe.
Maybe you just gonna go. But you're a beautiful artist.
I'll just do it like this so you can see. I don't care. I don't care. I don't care. Okay, what's our third ray we can draw? By the way, could we quit right there?
Yes.
We certainly could quit right there. I'm going to draw the third one just because. The third one should go from this point and line up with the center of curvature. Okay, so it should go like this, line up with the center of curvature, come up here, hit the mirror, and then bounce straight back. So mine's off.
Oh dear.
Mine's way off.
I have no mirror left.
Okay, you have no mirror left? If you have no mirror left, just extend your mirror out until it hits it. 'Cause mathematically, it still works.
Mine looks great.
I was thinking that.
Yours looks awesome. So my image should form somewhere in this region, in my little triangle. Now, let this be a lesson to you. When you draw it, even when you have a nice ruler and you're careful, sometimes your drawing won't come out exactly right. Okay? We're going to have a way to fix that in just a few minutes. Okay? Very good. It's supposed to go beyond C.
Inverted.
Okay, so it should look
Larger. Oh my gosh. Whoa. Fat.
Which way is it leaning?
all right. Now, good question. Which way is it leaning?
That way.
Okay, the closer in it goes, the farther out it goes here. So this is farther this way, so this will be farther this way. So it's going to look like this,
Oh.
or this, I guess.
How come it does that for that one? but not-
Okay, because general rule of thumb.
Do we really need to know that? Yeah,
I don't know.
Oh, you know what?
That's what I'm wondering.
You're right. Everybody? Okay. Notice when you're farther out this way, the farther out you go, the closer the image is in here. So if I move this object out this way, this is going to move this way, right? Okay? And as I move the object in, look what happens. As I move the object in, the image starts to move outward, right? So as I move it in, the image goes out. Okay. Since this is farther out, that means this is going to be farther in, right? Now look, see this? Since my chimney is on the outside, farther away, then my chimney over here should have been this way.
Even if it's at the exact same spot?
Even if it's the exact same spot, because watch what happens. Remember,
It spins like this.
it inverts your image, right?
Both ways.
Yeah.
Where's the ruler?
It cuts in half then.
So it flips it this way and this way. So it goes, what, like this, right? Yeah, so like my thumb's like this, it flips it over. Right? So the chimney's over here, the chimney will be over here.
Where's my mind making part? Because when we started doing that lab, the Lucy's lab, like Lily and them started to pull all these packages, and it's like complete, and I'm like, what?
Well, let's get ours done.
Done.
It's because y'all are so slow.
Sorry.
Thanks.
Sorry, not trying to ruin your self-esteem or
This is a
anything.
teacher.
Yeah, it's a teacher problem, right?
Always the teacher's fault.
Oh, whatever.
Yeah, I can do this.
Okay, let's describe this image. Let's describe this image. What's it like?
Inverted, real, beyond C and larger.
Inverted real. Beyond C. And larger. Okay? There you go. And how do we know it's a real image again?
Because it's on the same side of the mirror as
Because it's on the real side. Plus, does the light actually converge to this spot? Yes. Now you're going to see in just a minute what a virtual image looks like, and there's a trademark difference between the two. Okay? All right, so here we go. Now, everybody, don't draw this one. Okay, I'm going to put one on the focus right here. Okay, don't draw this one. Okay, now, if I draw a light ray that goes in parallel, it's going to come back through the focus. Now, notice I really have a hard time drawing one through the focus this time. Okay, so let's skip that one. Let's draw one through the center of curvature. So it lines up with the center of curvature, goes in, and then bounces straight back. Now look at these two lines. They're parallel. If they're parallel, do they ever cross?
No.
No. So therefore, no image forms. It's the only spot that you can place something in front of any type of mirror and no image forms. So what does it look like? It just looks like a blob of light. Okay? Yes, it's your vampire. It's the vampire spot. So no image right there. Okay?
Turn yourself invisible.
Well, when I see your face, it looks like a blob to me, but you use that.
All right, so here's our last one then. So no image.
I should have a haunted house.
All the mirrors are parallel or curved. Okay, here's our last one. Will you do this? And will you place an image right in front of here? And here, let's do a person.
With one of his either his left or right hand bigger than the other.
Or just take 3.
What's that? Oh, you can if you want. I'm just going to draw it symmetrical. Normally on the test, they don't care about that sort of symmetry. I haven't seen one except perhaps maybe a plane mirror.
That would just reflect it.
But a plane mirror is going to do this. It looks like it flips it front to back. Okay. All right, so here you go. First ray, in parallel, out through the focus. Next ray.
The object's blocking the light.
I know, but the math still works out. All right, next one. Line it up with the center of curvature. It goes in and bounces straight back.
Oh, but
Those are your two easiest ones to draw. C and F.
Really?
Yes. You could draw another one if you want.
Are you sure that's right?
I am sure that's right. Oh! I am positive that's right.
Okay, that looks cool.
I don't like going.
I don't like you either.
Excellent. All right, now, do you see this? Okay, do these two rays, will they cross out here?
No.
No, but are they parallel?
No.
No, so that means that they technically cross somewhere.
Beyond the mirror.
Okay. So where would they cross if they could?
Out there.
Out here. Alright, now this is the hallmark of virtual images. When the light bounces off a mirror and it diverges as it bounces off the mirror, not parallel like here, but diverges, then there is an intersection spot back here. The thing is though, did the light actually ever pass through this point?
No.
No. So that's the hallmark of virtual, where you backtrack the rays and it appears to our eyes to have come from there, but it never ever went through that spot. That's virtual. Okay? If you put a screen here, nothing shows up. Okay? So what's our image going to look like? Alright? Okay, everybody? Concave mirror. What kind of images form in a concave mirror?
Virtual
Yeah, virtual
and real.
and real. What kind of real images form?
Inverted.
Well, they're always inverted for a single, but look, it's mini-me
Or bigger.
to gigantic me, right? Mini, same size, larger, so all sizes can be produced. Small, same, larger. Okay, what about virtual though?
Only larger images.
Only enlarged images.
The virtual image, is that the same distance away from the mirror as the object?
Oh, great question. Let's describe this image. It's virtual, it's upright, larger,
And beyond the mirror.
Enlarged.
and beyond, or we might say on the wrong side of the mirror, or on the right side, or on the negative side of the mirror. However you want to describe that, it's over on the opposite side of the mirror where it shouldn't be. Okay? Now, Ian's question was, will this distance here be the same as this distance here? And the answer is no. It could be any distance. The closer you bring it into the mirror, the smaller this image will get until you're right up next to the mirror and it looks like you're the same, almost the same size. It's a little bit bigger still. As you move closer and closer to the focus, this thing gets farther and farther and farther away and bigger and bigger and bigger. Okay? You can get it to be a really huge image. Now, here's a kind of a crazy thing. If you're standing here, if that's you, can you see this image? Yeah, but you would be looking downward to see it, right? Because it would be below your feet if that's where you were standing. If you were standing here, could you see this image? Well, how about this one? If that's you, if you're this flower,
You could turn around.
but really, could you see this image? Because you're standing there looking in the mirror, and your image is back there, so you turn around to look there,
You just see
Look
something.
at you.
you won't see it.
Oh, it's
Why not?
Because the light rays are traveling this way, and you're looking that way. How do you see
What
things?
if you set up
Oh.
another mirror?
Yeah, the only way for you to see this is to put some other mirror back here to reflect it into your eyes. Does that make sense?
What if you put a piece of paper?
Now, if you put a piece of paper there, like a
You would see
screen,
it.
then it would show up on the screen and you could see it. Okay? Now, this is the odd thing about real images. Real images are out in front of the mirror. So there's the possibility that you could be closer to the mirror than your image and you won't be able to see it, but the people behind you can see it. Alright? Now right here, can you see this image?
Yes.
You certainly can.
It's
Okay.
there.
By the way, a lot of girls are familiar with this mirror.
Makes them look fat.
No,
One that you can see up close.
it's called a makeup mirror. Okay?
Doesn't make any sense.
It's the one where you get up close to it. When you're up close to it, it magnifies the size of your face.
Oh my God, the horror.
Excuse you.
Well, Christian was the one. Remember, he's looking at it. So
That's right. He is seeing his own image. So it's all right. Come on. You're a nice person. All right. Now, called a makeup mirror, and it's so it magnifies. Dentists can use that kind of mirror, like if they're doing surgery or something inside your mouth, and they have a hard time seeing inside your mouth. They can't just open you up because they'll break your jaw.
Yeah.
And so they could use a plain mirror, which they do, but they can also use a mirror like this and hold it up next to your tooth to magnify the size of the image so they get a better view of what they're doing. They could do that as well. Probably don't want to use one of these mirrors, right? To magnify it, because it would magnify it and put it upside down, making it very difficult
To
go in the right direction, right? Okay. Concave. Let's do convex. All right, find the convex mirror on your handout. Okay, ready? On your first one. I'll tell you why it's called a diverging optical device in a minute. This is called a convex mirror with light coming from the left. Okay? It's also called diverging. Okay, convex mirror or diverging mirror. All right. What's this point called? Focus. What's this point called? Center curvature. So it's exactly the same geometry. Open up your packet. It's on the back of the first page, or the last page maybe. It's on the last page. Okay? Okay, now, principal axis, everything's the same. Now everybody, you see this side? This side is the plus side. This is the minus side. Uh-oh. Uh-oh. Shh. That means that your focal length right here is a negative focal length. That's very important for when we do the math problems. Okay? Very important for when we do the math problems. All right. That's going to be really important. So mark negative focal length. Okay, the reason why it's a negative focal length is because it's on the wrong side. It's on the wrong side of the mirror where the light never gets to. Now, how do parallel light rays work this time? A light ray comes in like this, hits.
And then bounces.
Yeah, because look, the mirror is tilted this way, so it's going to bounce out and up, and it's going to bounce out and up this way. And it's going to appear as if it had come from the focus. So I want you to draw about 4 parallel light rays coming in, and I want you to draw them as if they have come from the focus. Okay, this is the other reason why we call this a negative focus, because it's a virtual focus. The focus is not a real focus because the light never converges to that point. It appears to have come from that point, but never really passed through the point. The hallmark of virtual. What's that?
It's a ghost. We're going back.
That's right, it's a ghost. Don't drop your bird. Okay? So a virtual focus. Okay, here we go. Here's my spot I'm going to start at. Okay, you ready?
Yes, sir.
Draw your light ray in parallel. Your light ray that comes in parallel.
Are you drawing on this one?
Yeah, on the bottom.
Oh, okay.
On the bottom. It comes in parallel. Oh no, where does this one go? Up and away from the focus because it's a mirror. And so it bounces out, up, out, and away from my mirror.
Next one goes to the front.
Okay. The next one, there's actually two you can draw. One is this one. If you draw it to the focus, so it goes toward the focus but never gets there because it's a mirror. And so it should bounce back which way? Horizontal. Okay? So if you go to or through the focus, it always bounces back horizontal. So there you go. Now we could quit there if we like, but there is a third one you can draw if you wish. It's maybe the easiest one of the batch. It has to do with the center of curvature. If you draw one toward the center of curvature and line it up with the center of curvature, it will hit
Bounce straight back.
perpendicular and bounce straight back, because that's along the radius again, right? So it'll bounce straight back. Now, those three, actually that's kind of wacky there.
Let's take that shot.
All right, notice the three reflected rays. One goes this way, one goes that way, one goes that way. Do you see that they all diverge? Okay, and sometimes it's a little hard to see, but let me erase this, and let me erase this, and you can see that the three that bounce off the mirror, it won't cross over here. So what we have to do is, but they're not parallel, right? So we just backtrack them to where they would cross. Backtrack, backtrack, and there is happy face. Okay, remember you only need two rays to draw this. And most students will draw the one that goes in parallel and then out, away from the focus, and whichever other one you want. Toward the center of curvature and back out, or towards the focus, and then, shoot, messed it up. Towards the focus, and then back out parallel, whichever one you prefer. Okay? What kind of image is this?
Upright.
Virtual upright what? Smaller. And this one is going to be on the wrong side of the mirror again, or behind the mirror. But this image will always form between the focus and the mirror. It's always going to form in this spot, right in here. Okay? Smaller, and then
Alright, so every every convex mirror will have to be the image between the focus and the mirror?
yes.
Is it all from this one?
The other day.
What do you think of like a motorcycle mirrors?
Okay, there you go. Now, that's it. That's all that this mirror does. Nothing more.
It's not tricky.
Okay? Now, you've seen these mirrors before.
Yeah, I know. They always catch me when I'm studying stuff.
Yes. If you're a kleptomaniac, these are the mirrors that you don't like. Because they're the ones that are up on the ends of the aisles at the grocery store or electronics store, or at the hospital, so you can see around a corner, right? And you can see lots of stuff in this mirror because it's all shrunk down, but it's all upright. Okay. If you're driving a car, the mirror that's on the front window, that's a plane mirror. The mirror that's on the right outside, the passenger outside mirror, objects appear closer, or objects are closer than they appear mirror. That's this mirror. Okay?
That is in fact true.
Okay?
They are closer than they appear.
They are closer than they appear.
I'm trying to think somebody else.
Okay? All right. It wouldn't be appropriate for us to have any of these mirrors in our car to see behind us because we don't want, based on where the car is at, for them to be maybe upside down. That would be bad. Right? Okay, so this mirror produces only one thing, virtual.
Upright.
Smaller. Virtuals, upright, and smaller. Hey, now look at this. Do you see? Virtual, same size right here. Virtual larger and virtual smaller. All three sizes. Three different mirrors. reel, all of the reels are right here with this one mirror. So this is our interesting mirror. These two are really quite boring. They only do one thing. This does a bunch of stuff. Okay? All right. Now, since we're on ray diagrams, let's go on to a lens. Okay?
Yes, sir.
Now, mirrors work on what kind of property? What's the... They work on reflection, right? Okay. Lenses are going to work by what optical property?
Diffraction.
Refraction, right? Refraction.
No, I'm not gonna color it. I'm not gonna write on it.
Okay, they work by a property called refraction. Okay? Now, go to, yeah, this page right here. Okay, everybody go to this page where it says convex lenses, converging optical devices, all right? We'll start right there. Now, mirrors are pretty simple because, like, if you have a mirror like this, it's really just a mirror like this, and a mirror like this, and a mirror like this. So light ray comes in and bounces this way, light ray goes in and bounces out, light ray goes this way and bounces this way. So you're going to have a focal point, right? And if you have a mirror like this, then it's like a mirror, mirror, and mirror. So the light ray bounces out, and bounces back. And so you're going to have this focal point back here, right? All right. Now, lenses work on refraction, so it's not reflection anymore. So, we have two distinctly different types of lenses. One of the lenses looks like this, and the other lens looks like this. Okay, this lens is essentially this. And this lens is essentially this. Okay? Okay, the hallmark of these two lenses is that this one is wide in the middle, skinny on the edges. This one is wide on the edges, skinny in the middle. Okay? Now, watch. Light ray comes in. Hits this prism. Here's my normal. Is the light ray going to turn up or turn down?
Down. Down.
Toward the normal, right? Comes out over here. Hits this normal. Goes from glass or plastic or something to air. Now which way is it going to turn? Up or down?
Down.
Okay, we're going fast to slow, so it went from big angle to small angle, right? Now we're going from slow to fast, so we should get an angle bigger than this one. If it goes up, what happens to my angle? It gets smaller, so which way is it going to have to go? Down. Down even more. So this one comes in, turns up, and turns up. And you get, guess what? A focus. So do you see why this is a converging optical device? Because it makes the light converge. Okay, what about this one? Light ray comes in, hits here. Which way does it turn? Up. Hits over here. Which way does it turn?
Down.
Down. It's going to turn up. It's because it turns toward the normal here and then away from the normal here. Okay, so down here it's going to go turn down and turn down. Oh, look at that. Two lines. They're going to diverge. We backtrack them. Look at that. We've got a focus. But what kind of focus is this?
A real focus.
No, it's a lens. So it's a
This is a virtual focus because did the light actually come from that spot? Does the light actually pass through this spot?
Yes.
Yeah, so there's my positive focus there.
Oh, sorry.
No physics taunting. All right?
Possible.
Now, so let's talk about this lens right here. This one's called a, okay, here's where we get into real problems a lot of times for students. Okay, what kind of lens is this? It's called converging, but it's called a convex lens. This is called a concave lens. Okay? Now, everybody,
Yes, sir.
how can I change the focal length of this lens? Where these lines are going to converge?
Make it thinner.
I could make the shape different, right? So I could make my lens shape like that. I could make my lens shape like this. I could make my lens shape like this. But in each case, do you see that they're fat in the middle and skinny on the edges, right? And so they're all going to have a focal point. Now that's one way to change the focal length of a lens, is to change its shape. That's how you change the focal length of a mirror, by changing its curvature or its shape. Okay, there's another way to change the focal length of a lens. Does everybody know how? I'll give you a hint.
Change
So
the
change the material.
Change the material. So this could be water, it could be plastic, it could be glass, it could be a diamond.
could be a
Hey, now wait a minute. If I change this from a water lens to a diamond lens, how does that move my focal length?
Sword. No.
Which one bends it more, water or diamond?
Diamond.
Diamond will have a bigger change in speed, right?
Bend closer.
So it'll
But then
bend
it'll
it
bend out.
farther inward.
pretty light.
Okay? So here's the deal. The higher the index of refraction of the material, the smaller the focal length is going to be for the same shaped lens. Actually, for both. And we had a great question. The question was, is if we change the index of refraction here to a higher number, what will that do with the focal length here? If the index of refraction goes up, the focal length goes in closer to the lens, no matter what kind. Okay? Hey, here's another thing. Shh. Some of you may have noticed this. Your eyeball works like this. Okay? We'll talk about it more. But if you have glasses and you go swimming and you put your glasses on and you go swimming, your glasses are cruddy in water. Why?
There's not air surrounding it.
Yeah, because it used to be air to, say, plastic, like 1 to 1.5, say, index of refraction, and it would bend a certain amount, right? But then now you're going from 1.33 water to 1.5 plastic. Okay, let's do our ray diagrams. They go like this. Okay, you see dots on both sides. Focus, focus. Focus, focus.
Negative focus.
All right, now. There will be a negative focus. Now, if we begin with our object on the left, draw a different object? Sure. If we start with the object on the left, then this will be our negative focus, this will be our positive focus. Why does a lens have two foci?
Because like left.
Yeah. Okay, here, I'll show you why. A mirror has two sides.
Well, only one actually acts.
Okay, yeah, a mirror, if this was a mirror, one side would be mirror-like, and the other side would not, generally, right? A mirror only has one side. But a lens has two sides, right? Okay, look through them either way, and it works. Okay?
So you take this. Where'd you go?
Now, everybody,
Why is it negative?
I'll show you in a minute. I'll show you in a minute. All right, everybody, look.
Okay.
Okay, this is called 2F, and this is called 2F. Okay, the reason why it's not called center of curvature anymore is because since a lens, the geometry of the lens matters.
It's not the center, anything.
Well, yeah, but the thing is because the geometry does matter, but index of refraction also matters, you can end up with, if it's like this,
There's no center out there.
then technically this is the radius to this side, and this is the radius to this side. But remember, if you have a lens that's like that, it also works just like this one. So you don't really have a center of curvature for the one side,
Did
right?
you see that death lens?
The what?
That death lens that they gave us in lab.
Oh, the great big huge one?
Yeah, that one.
And you had to figure out the focal point?
That piece of crap.
That was crazy.
That's
Jonathan
fine.
had that mug and we beasted, right, Jonathan?
You know how to find the focal length of a lens, right?
No.
No, you didn't show us.
No,
You never did it.
we didn't know. We didn't know. But
Losers!
but we figured it
Oh,
out.
thanks.
Bruin, you
I
didn't show
agree,
me
you
the
are
side, and you didn't tell us originally that the center of the curvature, I mean.
But I mean, it makes sense.
I don't know.
Alright, so here we go.
But we shouldn't have left from last year.
Light coming from the left. Oh, wait a minute, I forgot something. Draw a line down the center, called the lens plane.
Is that so that is right?
Yeah, so this is called the center of the lens. The center of the lens is where the principal axis...
You need a record.
No, I don't.
You stop complaining.
The principal axis and the lens plane cross. Okay? Now, if you have a parallel light ray, parallel to the principal axis, it comes in like this. Now, technically, it's going to turn twice. Listen, it's going to turn twice. At the front surface, it will refract, and on the back surface, it will refract, and go through this focal point. And you can do another one. It's going to refract at the front surface and the back surface. Now, look. Look. I'm looking.
I'm looking right now.
If you draw a line in straight all the way to the principal axis, and just make it turn at the principal, that's in principal axis, make it turn at the lens plane, and line it up. It's the same line as long as the lens is what we call thin, which means that it's about, the thickness of the lens is no more than about 10% of the diameter of the lens, okay? And we're going to just do thin lenses. So we can simplify our drawings by not having it turn and turn twice. We just draw it into the lens plane and then make it turn through the focus, okay? All right? It makes things simpler. All right?
Wait, straight to the center. And then
Yeah, so great. Go straight to the lens plane, and then from there, turn it through the focus. It's a simplification for your drawing. Okay? So notice that this, on the right-hand side, will be the plus side now. This is the plus side because notice this is a real focal point there. A real live focal point where light actually does converge there and actually passes through there. Okay? Now, that is opposed to this lens, where the lens looks like this. So go to this diagram. Go back to the diverging page and find this one.
stop thinking about word, Lisa.
All right, on this one, draw a lens plane. It's a little bit harder to draw, but draw your lens plane down the center of the lens. Forgot my L in my lens plane. All right. spelling's atrocious. Okay, now, everybody, look how this one works. A parallel light ray comes in, draw it all the way to the lens plane.
Why do you cook?
Quiet, you. I'm free-handing it.
That's pretty good.
I'd like to see you do better. You can't, so be quiet.
Rough stuff.
It's true.
Tough love. Tough love.
It's tough love. All right, now, where will these light rays go?
Out.
They will not go through this focus. They're going to go out and away. And away as if they have come from this focus. Okay, does everybody see why this is a negative virtual focus?
Yeah.
This is a real focus. Okay? Okay, converging versus diverging. Convex, right here, converging, concave, diverging. Now look, this is a bit confusing sometimes for students because guess what? Concave over here is converging. Yes. Convex is diverging over here. But over here, convex is converging and concave is diverging. So please work it out in your brain that you will remember this. Different students try different techniques to try to remember that the names are opposite.
Spat in the middle.
Yeah, however you want to remember it, I don't care, but you got to come to terms with it. Convex is so be careful. Convex lenses and concave mirrors are converging. Yes, it's the opposite. Convex mirrors and concave lenses are diverging. So they're exactly the same, but just the opposite. It's perfect nonsense. Actually, you're going to find that the drawings on all these are exactly the same. They're exactly the same except when they're exactly opposite. All right, since we're on the diverging page, let's go ahead and draw the one diverging lens picture. It looks like this. Hey, and just to show you that it doesn't matter, I'm going to draw a different shaped diverging lens. I'm going to draw it like this, where this one looks like, okay, if you see one that looks like this.
Don't freak out.
Freaking out.
Don't freak out.
What's that?
Where do you draw the line?
That's that. How do I know it's this kind of lens? Because the outside is fatter than the middle, right? So if it's skinny in the middle, it's one of these kinds. Right? I'm going to draw one just like that just so you don't freak out. Okay, you're going to have a focal point here. You're going to have a focal point here. If I place my object out here, you can place your object anywhere you want. What kind of object do you want? Somebody wanted something different.
Cow.
Kennedy, what do you want? You said, didn't you say?
Yes, she
You
did.
said draw a different object. What object?
A hamburger.
A hamburger?
Draw a square cow.
No, we're tired of square
Draw
cows.
a clown.
Draw a robot.
Hey.
Draw a clown. Robot.
What on mine?
Draw a square bird.
Robot.
Robot. Woo! Robot. Yes. Good sense of style. That doesn't look like a robot.
Draw a square bird.
Are you kidding me? That's Wally's cousin.
No, Wally! Wow.
I cannot draw that.
All right, robot.
I'm gonna draw ice. What is it?
Yeah, draw your spherical robot. Here we go.
Okay, purposely between two after that, or does it matter?
What?
Purposely.
Oh, yeah, actually where it's located doesn't matter. Okay, right here at the top of the robot, light ray comes in, gets the lens plane, and then where does it go?
Bounces out.
Stop it, Colin.
Like,
Where does it go?
Away from the focus.
Up, up, and away, because it's diverging.
What do we draw this at?
Towards the pin.
This is one of the hardest ones to draw. Light ray comes in parallel, hits the lens plane, goes up, out, and away from this focus, my negative focus. All right, now, the last one you can draw, or the easiest one to draw next, is the one that goes right through the center of the lens. Okay? Right through this spot. You can draw it and it'll go right like that and go straight through. Okay? Here's why it goes straight through. You see this side of the lens here? Right where it goes through, and this side of the lens right there where it goes through? Those two sides of the lens are approximately parallel. So they're like just like a window, a pane of glass. And the light that goes through a pane of glass, remember, goes like this. It will come through, refract, and then refract again, and it ends up going out along the same line almost. It's parallel, just offset a little bit. So this is going to come out parallel to the original one, almost along the same line. So just draw it straight through. Now if you want to draw the third one, please be careful. When you're dealing with lenses, if you've already used that one, you can't reuse it. Not like we did with mirrors. Remember when we draw one in parallel and it goes out and away from the focus? Our other one was toward the focus and then out parallel, right? So you draw it toward this focus. And then it goes out parallel. Now that one is pretty hard for students to draw. I really don't recommend it. You don't really need it. If you draw the two green ones, it's really pretty simple. Okay? But look where they all come from. They all diverge, but they appear to have come from this little robotic spot.
that's cute. Robot have pizza.
That's Ian's boyfriend.
It's mini robot.
Watch it.
Okay?
Oh, Richard.
All right. That's probably the hardest ray diagram to draw. I guess. I think it. I
Is it
seem to.
always between the focus and the...
And again, it will always be between the focus and the lens.
It's always going to be.
Hey, you know what? Guess what this is like? What's the properties? The properties are just exactly like this one. Virtual, upright, smaller. What are you doing here? So hey, look at this. This type of lens also produces the exact same kinds of images as this kind of mirror. Exactly the same. Except this one, the mirror forms them on the right, the lens forms them on the left. Okay? But otherwise, they're identically the same. Alright? Now, everybody, these are my glasses. And if you are nearsighted and you wear contacts, these are your contacts. Okay? How can you tell these are my glasses? Because if I move them out from my head, what does it make my head do? Makes my head look smaller, but still upright.
Tiny eyes.
Tiny eyes, that's right. Yes. Okay? Alright, so it makes your eyes look smaller. Okay? And it's this kind right here. Alright, let's do the more exciting one. Okay, any questions on that one? Virtual, smaller, upright. and it's on the wrong side of the lens, because light passes through a lens, right? So the images should form over here, but it forms on the wrong side of the lens, on the negative side. Okay, so negative side over here for images.
Oh, we never did.
Okay, so let's do the other ones. You ready?
If we had it here,
Here, I'll draw them bigger. F, 2F, F, 2F. Okay. What do you want this time for your object?
A foot.
A foot.
Frankensteinian.
There you go. We have a foot. A disembodied foot.
Beyond.
Looks like Rudy's feet.
Yummy.
How about bones?
No, I'm not going to draw a bone sticking out of it.
No goofy blood.
I know. I'm no fun.
Zombie foot.
All right. So, where will the image of our cadaver foot show up? Okay. We're going to pick a spot at the top again.
Blood coming out.
Okay, light ray.
Parallel.
Parallel in. I like that.
This thing goes.
Parallel in.
Oh, wait.
Lisa, where does this one go?
It goes in it, like on this side, but
On which side?
This side.
Which side is that side? I can't see your back of the room pointing.
when we had those two triangles, we had it going down.
And it'll go through which point? Which focus? Right or left?
Right?
Very good.
Yeah.
Okay, now. Okay? When you're on a test and you can't figure it out, it's like, okay, remember the little triangles and which way it's going to bend, right? Actually, that's a great way to do it. Okay? All right, so, Marcos, give me another ray.
Another ray.
Mm-hmm.
Try going to the center.
And then where will it go?
Keep going.
It's going to keep going, right? Because remember, when it goes through the center, right there, the two sides of the lens are essentially parallel, and it's going to go straight through. So it's going to go like this and go straight through. Okay, do you have a third one, anybody? Now remember, we have used this focus. So we have to use a different focus this time, right? So our other focus is we go through the focus, and then it'll go out parallel. Very good. So our image will show up right here. And let's see.
It's a foot. The foot will be facing the lens.
It's kicking the lens.
Look at that little. That looks like an arm.
Oh, be quiet. So it's going to look like that.
That looks like a hand.
It looks like an arm.
It looks like a...
Next time I'll draw a shoe. It's easier than a foot. All right. Okay, just to keep you all honest, I'm drawing a different shaped lens. This shaped lens is okay because it's still wider in the middle and skinnier on the edges, right?
Yes.
Okay, this time let's draw a mechanical cow.
No, the right cow.
How about a
Anteater. It's up.
Scrambled eggs.
That's not a duck. That's a
Here's the one.
cat.
Wow, that's not fun.
No, oh god.
What are
hey,
they?
we have a cat.
It sounds like a laser gun. The brewing set. Just put like a plate of lasagna. Garfield likes lasagna. I was trying to name son.
All right, hey, before we begin, let's start using our physics brain. Do you have a prediction of where this image will show up? On the paper. On our paper, thank you, Mr. Smarty Pants. Okay, hey, Which side? This side or this side?
This side.
Just do that.
Right side.
This side?
Yeah.
Okay, now where located?
At 2F.
2F?
Yeah.
Yes.
Inverted, same size.
Inverted, same size?
Yeah.
No.
That would be my guess. Inverted, real, same size.
Really weird.
Same
What do you do?
Good triangle.
Yeah.
This one.
It's gonna be close.
Other side.
What is
Oh, no. It's blue guy. That's, I want to get a better. Let's go.
Okay, you're seeing a lot of similarities between this one and the mirror, right?
Yeah.
It's the same.
That's a lot of opposites.
It's just on the right side instead of the left side.
It's virtual.
Hey, now you should see very huge similarities between lenses and mirrors. One big difference, though, is where the images form. Okay? In our mirrors that we drew, this was the real side and this was the virtual side, correct? But on a lens, since light goes through, since our objects are starting over here, this will be our real side and this will be our virtual side. Okay? So we swap sides of where the images form, but the images have the same behaviors as we had with mirror. With mirrors. Yes, ma'am.
What if we like draw the lines and they're not where they're supposed to be, but you know where it's supposed to be?
Okay, excellent.
Describe
The same side as well.
All right, now, everybody listen up. We had an excellent question. The question is, what happens when we draw our lines and it doesn't show up where we know it's supposed to be?
You fix it.
The answer is you fix it. Okay? So, how do you fix it? So like on this one, I just make sure, if I do that,
They call me lift and fix
so you just kind of rig it.
that.
Now, there's going to be a mathematical way for us to know exactly where each one's going to be. We'll do that in just a second. Okay? All right, you ready? All right, our next one. I'm going to draw my lens like this, just to keep you honest.
Between F and 2F.
Yeah. Right, a nice bland arrow. Okay, light ray comes in, goes through the focus. Light ray goes through the center, and light ray goes through the focus and then out. Oh, and mine's way off.
Rig it. Rig it.
I'm going to rig it.
Check your spacing, maybe.
Yeah, my spacing is off, I think.
Off.
Shut up. There we go. Better. Sort of. All right. I'm freehanding them up here, and I'm having trouble with my drawings on occasion. All right, notice that this image is real. It's inverted, and it's gotten much larger. And it's beyond 2F, right? Okay, we have one more to draw.
Draw pizza.
Pizza.
Draw a clown.
Draw pizza.
Draw an anteater.
An ammeter.
Anteater.
Oh, an anteater.
Draw a book.
Draw an anteater.
Draw a book.
With
Draw
big
a porn
nose.
star.
And name him Rudy.
Book.
Rudy.
Porn star.
Draw a circular house.
Don't make fun of him just because he likes to dance.
Draw a ring.
You made fun of me at the beginning of the year. You had the markers, and then you were like, this
Draw
is
a
the
big
go bouncing
spot.
off. Whoa, you got a big nose.
That's an anteater.
Yeah.
No, he gives me pauses and he's like,
All right.
No, look at you.
Hey, If I put my object on the focal point,
No image.
no image because the light rays will go through and come out parallel. So I'm going to draw one in here, and here you go, an anteater. All right? Sorry.
Oh, yeah, so
We're running out of time. Okay, light ray comes in like this. Where does this light ray go?
Where's the focus?
Towards the vagina. That's the focus.
Oh, I missed it. Okay, where does our next one go?
To the center.
Through the center. Now look at these two light rays. They are not parallel, but they don't cross out here.
So you have to fake it.
So we have a fake image, which we call in science a virtual image.
Virtual image, large, upright.
Okay, so virtual.
Is it beyond?
Actually, it could be anywhere back here. Virtual, larger, upright. And then on the left side of lens. Okay, or on the wrong side of the lens. Okay, here we go. You ready? Okay, let me label these. I forgot to label them. Okay, if this is lens number 1, lens number 2, lens number 3, and lens number 4.
You should do like a random one, like 6.
Okay, and lens number
6.
12. Okay, which one of these is your eyeball?
Your eyeball inverts it.
Your eyeball inverts it, so it's got to be 1, 2, or 3.
Number 2.
Pick 3.
Pick 3.
Okay, let me ask you this, because the question is that it's like, well, is the image the same size? Let me ask you this. If you're looking at a mountain or a person, how big is the person and how big is the back of your eye?
It has to be smaller.
The person is bigger than
Hopefully the person or the mountain is bigger than your eye. And so which one does it have to be? It has to be number 1, because your eyeball is like this. And the image has got to form tiny because you don't have an eyeball this big. Right? So it makes small. Quiet. All right, now which one of these is a magnifying glass?
I'm going to go with 3.
But it doesn't invert.
Number 3, you're telling me that when you have a magnifying glass to look at something, that you have to flip it over for it to be upright?
Yes.
Yeah.
No!
Is that weird?
4.
Should that not be happening?
It's this one. It's this one. Because when you use a magnifying glass, it's larger but upright. Okay, which one of these is a movie projector? Stop
It's
it.
bigger, it has to be divergent.
It's 3.
How big is the screen?
Bigger.
How big is the film?
Smaller.
Film, screen. Uh-oh.
They put the film in upside down.
No, your seats are upside down.
I knew it.
Okay, yeah, they put the film in upside down so that it comes out right side up. Or they could put another lens in.